Okay. So we did write the expressions here for the gimbal, spin, and tangential axis. So I'm going to take the rate of change with respect to the spacecraft. This will allow me to compute how CJ is changing, because as we said, it is changing. So the rate of change of the TJ axis, for example, with respect to time seen by the body. So in the body axis, the only the gamma angles are really changing, right? So I have minus sine of gamma j, ATJ 0, minus cosine of gamma j, ASJ 0, and this is multiplying gamma j dot, and you can easily see that this is equivalent to writing minus ASJ gamma dot. For the spin axis, we have rate of change of ASJ with respect to time seen by B is a minus sine of gamma ASJ0 plus cosine of gamma j ATJ0 multiplying a gamma j dot, and this is also equivalent to writing ASJ gamma j dot. Okay. Something is not right. Cannot be. This is a TJ. Okay. Sorry about that. And then finally, rate of change of AGJ with respect to time seen by the spacecraft is 0. Okay. So if you keep this in mind, then you can get the CJ dot. You can show to yourself that it's CJ that multiplies this matrix. Okay. Another way to write this can be that it's equal to CJ omega J with respect to body skew symmetric matrix. Okay, because that's really what it is. The angular velocity of the assembly J with respect to the body is really just an angular velocity about the G-axis. That's the only rotation that I have. Well, if I don't consider the wheel, of course. I don't consider that it's spinning. The axis associated with the J assembly, they rotate with an angular velocity that is given just by gamma J in the direction, gamma J dot in the direction of G. Okay? Is this making sense? Where is this coming from? Okay. You can also prove that the following relationship holds, that CJ dot transpose is equal to minus omega J B skew symmetric matrix times CJ transpose. There's not much, to be done to prove it. Just transpose both sides of this relationship here. When you transpose the skew-symmetric matrix, you change its sign. So really, that's what it is. Okay, now to derive the equations of motion for the spacecraft with these objects inside, we need to take the derivative of the h. So, and all these terms that we have computed will help. Sorry, the cable is in the way. Okay. All right, so, well, let's start with the first term. So basically, I need to get to an equation like this, right? I need to compute the pieces of this equation here. So I'm going to start with the first one, rate of change with respect to the body for h. Okay. Rate of change. Yes.
The minus sign in this expression is coming from the fact that we are computing the angular velocity of J with respect to the body, because if we do C dot transpose times C, then since C dot transpose this C to the minus 1, we obtain minus omega, and I don't really understand the sign.
What, this one?
Yes, because C dot C is omega, right? C dot transpose C.
Okay. I mean, do we agree with this expression here? To begin with? The Cj dot is Cj that multiplies the omega skew-symmetric matrix.
Yes, I think so.
Okay. So if I transpose both sides of this, when you have matrices and vectors that are multiplied and you transpose, you invert the order and transpose, right?
Yes.
Okay, so this is why Cj becomes Cj transpose. And when you transpose a skew-symmetric matrix, you basically just, if you change the sign, it's the same thing. Agree?
Yes, right.
So that's why I have the minus. Yeah. Just look at this matrix. If you transpose it, you're gonna end up with the minus here and the plus here. So it's transposing it, it's equivalent to changing the sign to the whole matrix. And that's true for any skew-symmetric matrix. Okay. So let's see what this is. Now this is going to be interesting and a lot of calculations. J plus the summation of the Cj's, Yj's times Cj transpose omega dot plus summations of the y about the gimbal axis gamma j double dot now, because I had a dot before, Cj that multiplies 1, 0, 0. Then I have summation of I SJW, the moment of inertia about the spin axis, capital omega j dot, Cj 0, 1, 0, and I'm not done. Now I have to take into account the rates of the CJs, basically. I haven't done that. So for the first one, so basically I take, well, let's go back to what H looked like. I think it's easier if we do so. Okay. Number H was this expression here, right? So I'm taking its time derivative with respect to the spacecraft first. Then I taken the time derivative from this term, the one component that has the time derivative of omega, for these other two only the time derivatives of the angles. So now these are all products, so I have to take care of taking the time derivative of the parentheses for this term of G and S axis for these other two terms. These are constants. So okay, so for the first one I have, well, J is constant within the spacecraft, so all it's left is taking the time derivative of these terms here. So that will give me summation of, first I take the time derivative of this, so Cj dot, we just show to ourselves what that is, so that's going to give me Cj omega J with respect to the body skew symmetric matrix Yj that multiplies Cj transpose times omega b, omega, we just called it omega, and then I have plus minus, let's see, summation of Cj Yj. Now I have omega, something is missing here, 1 second. No. Okay. JB, again, J with respect to B, X, CJ transpose times omega. So these two terms take care of taking the derivative of this total moment of inertia of the spacecraft plus the assemblies, plus the momentum of switch devices. And then I have summation of YGJ, the gamma dot, and then I have Cj omega J with respect to the body skew symmetric matrix that multiplies the vector 1, 0, 0, and one last term, which is summation of ISJW that multiplies the spin rate of the wheel Cj omega J with respect to body skew symmetric matrix 0, 1, 0. So I've used, in doing these expressions, Cj dot is Cj omega of the assembly with respect to the body skew symmetric matrix, and Cj dot transpose. These are the two expressions that I've used to derive these terms. Okay. Now we can also see that there's some simplifications here. Cj that multiplies omega J with respect to the body skew symmetric matrix and then 0, 1, 0. Well, this is equivalent to gamma J dot Cj 0, 0, 1. Just a function of the fact that this is a skew symmetric matrix. We'll shuffle the order of things here, and so that's what you're gonna get. You can easily show that. So there's one thing here, and then Cj omega of the momentum exchange device with respect to the spacecraft in skew symmetric matrix form that multiplies 1, 0, 0. Well, this is just a bunch of zeros. Just keep in mind, for example, if you multiply this skew symmetric matrix times this vector, there's no elements here that are non-zero that multiply the 1. So basically, you get a 0 matrix. And so the fact that Cj is there doesn't matter anymore. Okay, and then there's more. We can So let's see, we can write this ugly term here, Cj dot Yj Cj transpose plus Cj Yj Cj dot transpose, which is coming from taking the derivative of this term, right? This summation here. It's just one of them. Well, we did write already that this is equal to, let's see, Cj omega j with respect to the body, skew symmetric matrix, yi. No, we didn't write this. I'm writing it now. Cj transpose. So do we agree with this? Okay. Plus Cj Yj, and then I have minus omega jb, oops, jbx, that multiplies Cj transpose. So I can collect, see there are similarities, I have Cj, Cj, C transpose, so I can rewrite this, and it is going to be Cj that multiplies the omega j with respect to the body skew symmetric matrix that multiplies just this component, this matrix here, the matrix of the assembly, minus again the matrix of inertia of the assembly, j omega jb skew symmetric matrix that multiplies Cj transpose, and then, well, we're gonna see what it looks like. It's gonna take a little bit of unknowing work, but it's going to be useful. So bear with me. I'm going to actually write what these things are. So remember, the skew symmetric matrix here is just simply, so this term here, it's a bunch of zeros everywhere. I don't even remember what it is, honestly. Oh, it's a minus gamma j dot here, and 0, and a gamma j dot here, and that's it. So it's a very convenient matrix to multiply other things by, because it simplifies every other term. So when you multiply it times these, all you're left with is the elements that are here and here, really. So in other words, these can be written as Cj that multiplies this matrix here. Let's see, 0, 0, 0, 0, 0, minus gamma j dot, the moment of inertia about the tangential axis. That's all it's left. Then I have 0, gamma j dot, the moment of inertia about the spin axis, and then 0, minus a similar matrix, 0, 0, 0, 0, 0, minus gamma j dot, moment of inertia about the spin axis, and I have 0, gamma j dot, moment of inertia about the tangential axis, 0. And then here I have Cj transpose. Okay, we're getting there. We have Cj. I can put all these together and it will look like the following. Bunch of zeros, we like that, we like zeros. We have gamma j dot, and the difference between the moment of inertia on the spin axis and the moment of inertia on the tangential axis. And then I have another 0 here, and a similar term, gamma j dot. Here we have, well, the same thing. Tj 0, and let's not forget that we have a Cj transpose at the end that barely fits into my paper. Okay, I can actually collect this scalar part, put it outside. It's a gamma j dot y sj minus y tj. What is this multiplying? Well, this is multiplying Cj, and we said initially that Cj was going to be the gimbal projection on the axis of the spacecraft, of course, the spin and the tangential, right? Well, this is going to multiply now a matrix that has 0, 0, 0, 0, 0, 1, 0, 1, 0, and of course it doesn't fit in here, but it will be the same matrix, just that the G, the S, and the T are, so I'm gonna write it here. It's multiplying basically a matrix that looks like this. The GJ is now like that. S is a row and T is also a row. Okay. All right. So if you multiply this matrix with a bunch of zeros times this one, it removes the first row. So you're left with gamma j dot moment of inertia about the spin axis minus moment of inertia about the tangential axis. The Cj matrix is still there. Okay, while the product between the last two matrices is giving me nothing on the first row, and then I have Tj and Sj actually. So multiplying times a matrix like this will erase the first row and also swap the order of the other two. Okay, nothing special, but I'm not done. This is equal, equal. I am going to actually spell out the terms here. I have gamma j dot ysj minus ytj. So what do I have here? I have g, j1, 2, and 3, and then same for the other ones. Remember, these are the projections of those axes of the momentum exchange device in the body of the spacecraft. These are functions of gamma. They change with time. They change according to our control law, which we haven't explored yet, but we will. This is TS3. Then I have SJ1, SJ2, and SJ3. And finally, I'm going to get a super ugly expression, my opinion, but we need it to be able to code this eventually. I promise I will go back to where we were and summarize why we're doing this. So I have 2SJ1, TJ1. Then I have SJ2, TJ1 plus SJ1, TJ2. Then I will never fit in here. Let me do it like this. Sorry. Okay, let's do it again. I have J, gamma J dot multiplies YSJ minus YTJ, right? Now the matrix. Let's do it again. 2sj1 tj1 sj2 tj1 plus sj1 tj2. Then I have sj3 tj1 plus sj1 tj3. sj1 tj2 plus sj2 tj1 twice sj2 ts2, and down here I have sj3 ts2 plus sj2 tj3. These are all projections, these are all scalars, okay? These values I'm writing down. Of course, they need to be scalar. tj3 sj3 tj1. Almost done. Okay. And I barely made it. All right, so that is your ugly thing here. Which can be expressed in a more compact way, much more compact, other than this term gamma j dot y s j minus y t j. This matrix can be expressed as tj, the actual three components. Imagine it as a vector, right? That multiplies sj transpose plus sj tj transpose. So take basically this expression will look like what you would do is you would do tj1 tj2 tj3 multiply times sj1 plus sj2 plus sj3. This gives you a 3 by 3 matrix. Then you do the same with this other operation here, another 3 by 3 matrix, add them together, and you will see that you get these these basic terms that I wrote on top. Not the funniest thing, but after having done this, I go back to my, I find it. So, you know, this is what I was doing. I was focusing on this term here, cj dot yj cj transpose plus cj yj cj transpose dot, because in my derivatives here, they do appear, right? It's here, and it's here. So if I use this expression, my angular momentum time derivative is going to look like the following. So now I'm going to actually write the whole thing. hc time with respect to the body. This is what we were doing, and I'm going to rewrite it in using this expression that I just found, and then I have omega body with respect to the inertial that is crossing hc itself, and this is equal to external moments, right? Okay, so now I'm going to put it all together. This first term is going to be j plus summations of the cj's, yj's, cj transpose omega dot plus, no news here, summation of the y gj gamma j double dot gj plus summation of isjw gamma j dot sj. Then I have the summation of the moments of inertia about the wheel, about the spin axis of the wheel, gamma j, I'm sorry, omega j gamma j dot tj. And this is coming from this simplification, if I can find it, that we made, one of the three observations that we made. Where did I put it? 1 second. Okay. That's pretty much coming from here. If you take Cj and you multiply it times the vector like this, you only are conserving the last column, which is Tj. Okay, so this is basically the vector Tj. So that's what this is coming from. Okay, so at least I'm using what I've derived, right? And then plus, and then remember there was the second thing we have, second property we found, this one, that Cj times omega j with respect to b skew symmetric matrix applied to 1, 0, 0 is 0. So this term goes away. Do you see it? So this term will go away. Okay. So what am I left with? Well, I'm left with this summation. The third prop. So I've used those two observations. Now I'm using the last one, the one that took a little bit to calculate, which is telling me gamma j dot y sj minus y tj, and this will multiply this matrix and omega. And then, well, this takes care of everything in the first term. Now I have this cross product, so I'm going to do that. That's omega x applied to j plus summation of cj y cj transpose omega plus I have summation of ygj. You're not falling asleep, are you? Gamma j dot.
No.
Okay, go omega x. I'm almost done. Gj. So this is cross product of omega times, this term here, and then the last cross product is with this other one. Omega j, omega x, sj. And this is equal to the external moments, or well, this is a projected. Anyways. So these are your general equation of motion, the kinetics of a rigid body that is mounting momentum exchange devices whose gimbal angle can change, and also the rotation of the wheel can change in terms of its rate. So this term is this parenthesis is the total angular momentum. I'm sorry, moment of inertia of the spacecraft. This is the contribution due to the acceleration of the gimbals, contribution due to the acceleration of the wheel, and then other terms that are byproducts of having used the transport theorem. Now these equations, they better collapse to Euler's equations when we stop all these momentum exchange devices, we prevent them from moving. And let's see, they do. if the S, T, and J's, we lock them in place, they don't change. Well, this is not a variable matrix anymore, so you can collapse this into just a J. This goes to 0, gamma J double dot goes to 0, omega J dot goes to 0, this goes to 0, this goes to 0. Again, this will be omega cross J omega, and all these other terms go to 0. So yeah, they do collapse into what we've seen before if the gammas and the omegas cannot change, or rather they are 0. Okay, questions? A little tedious, but that's what it is. So now let's look at the different options that we have. Option number 1 is the simplest, very much used in practice, reaction wheels. What that means is that gamma J dot is 0. The gimbal is locked. You can't really change the axis of spin inside the spacecraft. So as a consequence, all that was making the CJ change was really the gamma, right? Remember that the equations we wrote for the axis T, S, and G, they are just functions of gamma. So if gamma doesn't change, I mean, they're locked. It's not a function of time anymore. So meaning that J plus summation of the Cj, Yj, Cj transpose, I can just call it total J, and it's a constant. It doesn't change anymore. And go to the big expression we just computed for the final equation, and you will see, oh, it's just behind. So setting all the gamma dots and gamma double dots to 0, your equations of motion collapse into J total omega dot plus omega x J total omega plus summation of I S J W gamma J dot about the S axis plus summation I S J W omega J omega x S J equals external moments. Again, here I'm not underlining vectors, etc., but this is a matrix, this is a vector, matrix, matrix, vector, scalar, scalar, vector, scalar, scalar, matrix, vector, vector. Okay. So this would be the equation of motion of your spacecraft with reaction wheels. What do we do in practice? Well, in practice, we control this variable. This is what you do with reaction wheels. You spin up or spin down the wheel to obtain that term that is really your control term. And you know, there's control laws that you can develop based on this equation, and we will see that. An example is, which is usually the first thing to do, is how we would use reaction wheels to keep null motion. So basically omega equals 0. Well, just plug in omega equals 0, and you see that the term with the gamma J dots has to be equal to the external moments. So if there are disturbance, torques, something that comes from the outside, you do counteract it with the wheels. Now these wheels, as we said, they are physical systems. They are discs mounted on your spacecraft. Okay, they spin about the S axis. Actually, we call this AS. Okay, this is the omega j, and they're mounted inside the spacecraft. They are physical systems, which means that the omega j dot has to be the norm of it has to be less or equal than some omega j dot max. There would be an electrical motor, an actuator that accelerates the wheel, and how much you can accelerate it, it's obviously limited by the actuator physical properties, by its design. Likewise, the spin rates cannot really go past some maximum RPM. You can't spin the wheel up indefinitely because it's a physical system and there are bearings and they have limits. So one problem with reaction wheels often is what we call saturation. In other words, for some reason during your maneuvers you have accelerated one wheel one way or the other and it's reached the maximum and you can't use it anymore. Or if you want to use it, you have to slow it down, bring it back to a nominal RPM value. But if you slow it down, that means you apply some omega j dot. So you are upsetting the orientation of your spacecraft to desaturate the wheel. So what is usually done is exactly what's described in this equation here. Say that your spacecraft, you don't want to perturb the motion of your spacecraft, maybe it's at zero angular velocity, but you need to slow down the wheel, so you have to actually apply some non-zero omega j dot. Well, what it's done is that you desaturate, so you start slowing down, for example, that wheel, but you need to compensate for the torque that it's creating. And so that's done with thrusters or maybe with your magnetic torquers. So that is one problem with reaction wheels. They have, as everything, physical limitations, and if you are not careful enough in the way you're using them, if you don't keep into account in your control law and your maneuvers their state in terms of RPM, you can reach the maximum, and once you're there, you need to desaturate, and that creates a torque, and so you have to compensate for that torque, and that's a problem. Okay, so that is one case, the simplest. Then the second one, which is also very much used in practice for agile spacecraft, it's the CMGs, or control moment gyros. In this case, we actually don't allow the wheel to spin up or down. The gimbal is moving, but the wheel cannot change its RPM about the S-axis. So I'm going to rewrite the expression here. Maybe, yeah, let's do it. J plus summation Cj Yj Cj transpose omega plus summation Ygj gamma j double dot Gj plus summation Isjw gamma j, omega j gamma j dot Tj. Then I have, these are the term here. This is gamma j dot, that multiplies Tj Sj transpose plus Sj Tj transpose omega, and then the cross products J plus summation Cj Yj Cj transpose omega plus summation Ygj gamma dot omega x Gj. Finally, we have this term omega b ISJ, and this is equal to external moments. So not much nicer than the previous one. There's a few terms that go away, but that's what you get. Now, again, null motion, just to highlight what you get from the CMGs, really. If you put omega to 0, the omega of the spacecraft, you're left with summation of y, g, j, gamma j double dot, gj plus summation isjw, omega j, gamma j dot, tj equals external moments. So, you want to keep your spacecraft at 0 angular velocity, you have disturbances, this is how you have to control your CMGs. So this is really not actually used in the control design approach. So this actually usually go into the disturbances because the moment of inertia about the gimbal axis is quite small by construction compared to the moment of inertia about the spin axis. So it's really not that useful. And it's considered, a disturbance. And plus, you will have to control the acceleration. That's not usually done in practice. You don't control accelerations with actuators, really. So, so basically, it's like that term didn't exist. The one that is really important is this one, because this term shows what it's called the torque amplification. Think about what's happening. You have your wheel that is spinning at a fixed rate, 500 RPM, whatever it is. This is the biggest moment of inertia you have for your momentum exchange devices, the spin one. And you are multiplying these times the gimbal rate. So for a relatively small gimbal rate, you can obtain pretty big torques, definitely bigger than if you were just using a reaction wheel. So the advantage of a control moment gyro is there are several. They usually give you more torque for the same size of the spinning wheel, which means that for the same torque you can actually have smaller wheels. They require less power. You're really just maintaining the RPM of the wheel and changing slowly the gimbal position. And so there's less volume, less mass, less power for the same torque. So they're usually advantageous from many points of view. The disadvantage is that you have to control them. So you have now to maintain not only the spin rate fixed for the wheel, so you have an actuator right there. You also have the one on the gimbals. So mechanically speaking, they're more complicated to build and drive, of course. And then the last one is the variable speed control moment gyros that BS CMGs. Now, to my knowledge, these have not been used in space. You can find a lot of publications about this concept. For example, Professor Tsiotras from Georgia Tech, when I was working on my thesis that I shared with you, he was into this BS CMG business. And there's some interesting publications out there. The beauty of this is that you have more degrees of freedom. The equations for the null motion are the following. You have summation of y, gj, gamma j, double dot, gj, plus summation of I, s, j, w, gamma j dot, sj, plus summation is j w omega j gamma j dot tj equals to external moments. So this would be for, of course, omega of the spacecraft maintained at 0. So again, we don't really use this term, okay? So this one is kind of useless. It's you can call it a disturbance. What's the advantage? Well, one thing that I did not mention for CMGs is that you may still have some problems. Depending on how many you have on your spacecraft and how they are mounted, you may end up with all these tangential axes for the different CMGs pointing in a way that doesn't actually satisfy this equation. So you may have a required torque that you cannot exert because you move them around throughout your maneuver, and they end up, the t-axis end up in a configuration that is called singular. In fact, there are control laws that try to avoid that. That while you're controlling orientation, performing a slewing maneuver, whatever it is that you're doing, you also keep an eye on not ever making T's parallel to each other, for example. And so there are additional constraints to the design of the control law that can try to handle the problem of singularity. But the beauty of VSCMGs would be that, well, this is the CMG term, right? Okay, if this is for some geometrical reason not able to give me the torque I want, I don't care. I have the reaction wheel term. So basically, you know, variable speed quantum moment gyros are nothing more than thinking about combining CMGs and reaction wheels. As I said, to my knowledge, they've never been used in space, because if CMGs are difficult to control and complicated, these are even more complicated. But there are more degrees of freedom. In other words, your control variables are more now. Now you have the velocities of the gimbals and the accelerations of the wheels. And some publications, as I mentioned, from Georgia Tech, for example, not only them, but that's the first that comes to mind, they propose control laws that integrate attitude control and power storage. In other words, you use the CMG, and as long as the CMG term is not singular, you can use the sum of the wheels spin rate, kinetic energy to accumulate power. And so when needed, you can release that power in the form of electrical energy. So, I mean, it will be a very complicated thing to build and to control software-wise. But, you know, having more degrees of freedom allows you to do more. So it will be power, attitude control, and power storage and release when needed. But that's really, you know, topic for a PhD dissertation, and it's really it's really complex to realize. But I'm sure that eventually we will see some try to build them and fly them on CubeSats to begin with. So okay, now at this point we have the equations of motion for everything together, please. And well, it is time to close the loop. So far we've seen torques that are passive, semi-passive. We try to design some kind of feedback, as you've seen with the magnetic torques, but there's so much we can do. Well, now we have a lot of variables in here that we can actually use. For a VSCMG, again, we have the capital omega J dot and the gamma dots. Those are the things that we control. So what if we have a desired, like you're starting to build a desired quaternion and a desired omega that we want to track? How do we command these variable speed quantum moment gyros, or just CMGs, or reaction wheels, so that we track the trajectory? So let's see. We have two choices now. I think I can press on. Maybe I should deriving the controller. I have a version. I mean, this is not the only possibility. I have basically the one described in my thesis. I think it's very similar. It's based on the Lyapunov theory, and that will give us a way to implement a feedback loop. And then, so we can continue and try to finish this up now. And then later we have 2 more hours. My suggestion is that we start building, forgetting about the feedback loop, we start building the blocks to simulate the momentum exchange devices, which really starts from, well, the first thing to do would be, as we will see, of course I lost them. Well, implementing these, the position of the axis of principal inertia attached to the momentum exchange device, and then build all those matrices that we have seen for the equations. Sounds like a plan? So, in other words, what I want to do is derive a Lyapunov-based controller for a spacecraft equipped with really just MEDs, okay, momentum exchange devices, to be generic. Okay. I'm going to write the candidate Lyapunov function here. That's how we start, and then take another couple minutes break. I know this is theory heavy today, but this will put us in a very good shape to actually work on the big assignment. So let's say that we define some, let us define a desired motion and I call that omega desired and Q desired, exactly like we've done yesterday in Simonic. You have a desired quaternion and a desired angular velocity that goes with it. Okay, my candidate Lyapunov function, I'm going to start from there. How many do not know Lyapunov control?
Yeah, I don't know.
Okay.
Me.
So it's well, we'll see the conditions, but basically what we do for with Lyapunov control, you try to derive a controller that makes your closed loop system, your controlled system, Lyapunov stable, and we've seen what Lyapunov stability means in a few slides yesterday. But it boils down to defining a scalar positive definite function called Lyapunov function of the error, usually, that your system experiences, and we want to make the time derivative of that Lyapunov function always negative definite by acting on what we can act. In our case is capital omega j dot and the gamma j's. In other words, you're building a function that over time, this is your V function, that represents in a sense the error of your system in tracking whatever it is that it's tracking, and you want this function to do something like this, to go down asymptotically to 0. That's really the goal of Lyapunov control in a nutshell, very high level. And so the difficulties of Lyapunov control is writing a good candidate Lyapunov function. That's really the difficult part, because that drives everything else. But it happens that I already have it for you, so I'm proposing the following. 1/2, the error in angular velocity transpose, J total. Remember, this was J plus those summations of CJs, YJs, CJ transpose, okay? That multiplies omega error. This is a matrix. Of course, I'm going to drop all these things in a second. Then we have, I'm going to tell you what this is. A portion of the error quaternion, transpose that multiplies itself, plus, so these are the vector part of the error quaternion, and then we have this term 1 minus the scalar component of the error quaternion squared. That's my candidate Lyapunov function. So where, let's see, omega error is omega of your spacecraft minus the omega desired, and the error quaternion is given as well, the vector component that I call E and the scalar component that I call E4 transpose. You can also spell it out as E1, E2, E3, E4 transpose. And so this is nothing more than, for example, what you did yesterday, extracting, putting together the DCM between your body and the LVLH, and then extracting the quaternion. It's exactly the same. In this case, you will have a DCM that is given by your desired quaternion, the DCM of your spacecraft. You multiply them together, you extract the quaternion. That's the quaternion error, is the difference between your orientation and the desired one. Okay. So that's my candidate Lyapunov function right there. And I'm also going beyond, and I'm saying that I would like to force my system to do the following. I want, so this is something that I'm hoping to obtain. I want to have the Lyapunov function time derivative, and it's a scalar function, by the way, to be following this law: minus omega error, k omega omega error. And this is a definite positive matrix. So with the minus in front, this is giving me a negative scalar. So this is definitely negative definite. So negative definite for definitely for omega e. But what if let's see. Okay, so this is always, I'm sorry, this is always negative definite, okay, in general. But for what happens when I have omega e equals 0? I need to verify, need to check what happens to QE. Do we follow why? So I have defined the Lyapunov function that is a function of everything. The tracking error in general, the error in angular velocity, the error in orientation. And I am saying, well, I would like my Lyapunov function to have its time derivative doing this. And that's fine. That's always good, as long as omega e is non-zero. I am satisfying the Lyapunov condition that I have a positive definite, in this case, quadratic Lyapunov function of the error, and its time derivative is definite negative, negative definite. So I'm fine with that. But then if my error in angular velocity goes to 0, which I'm happy to obtain because that's one of my goals, well, I don't know what's happening to QE. From a high level perspective, what this is telling me is I have controlled my spacecraft to drive to 0 the angular velocity error. But what about the orientation? Because you may be tracking an angular velocity perfectly, but you may be pointing the wrong way. So you need to make sure that what you were doing here is not going to forget QE. Okay. Well, what you do in this case is that you start taking more derivatives. So theory tells me that the first time derivative of odd order one, 3, 5, etc. computed at the omega e equals 0 should be negative definite. And I would say the first next time derivative, because this is the first. Then we keep going, and if the third one is fine, we're happy with that. Okay. So if that happens, it's a sufficient condition. If this happens, it's a sufficient condition for stability on QE as well. Okay. Well, let's see if that works. If I take the second time derivative and then the third of my d, if I wanted, as I said, v dot to be minus omega error transpose k omega error, and please notice that I'm dropping all the underlines at this point because it's easier for me. But this is a vector, this is a vector, and this is a matrix. V double dot is equal to what? Minus 2 omega e transpose k omega e dot. Easy to show, right? K is a constant. V triple dot is going to be minus 2 omega e transpose dot k omega e minus 2 omega e transpose k omega e double dot. I know I said I would take a break, but it doesn't look like I'm doing it. Let's try to press on this. Remember the candidate Lyapunov function? That was actually, what did I write it? Right here, this. So this was my Lyapunov function candidate. How about I take the time derivative for this? Let's do it. So this is from V, from the actual definition of V. It is 1 over 2 omega error transpose J total dot. Remember that this has momentum exchange devices, so the J is actually possibly changing. Plus, let's see. I think I'm missing a 2 somewhere. No. Omega E transpose JT omega error dot. Yes. So so this is coming from taking the time derivative. So the first one is pretty easy, right? It's taking the time derivative of this product, only the time derivative of J. And then I have to do the same, taking the time derivative of this vector and then this vector. You do it twice, you have an omega E transpose dot, and then you have an omega E dot. You can, since this is a scalar, everything is a scalar here, you can transpose it. Let me do it on a separate paper just to show it. So basically, the rate of change of this term, 1 over 2 omega E transpose JT omega E. If I do it, it's going to look like, well, 1 over 2 omega E transpose JT dot, which is the no-brainer where the derivative is of the matrix of inertia. And then I have two terms. I have 1 over 2 omega E transpose dot J transpose, J total omega E, and then 1 over 2 omega E transpose J total omega E dot. So what I'm claiming is that these two are equivalent to omega E transpose J total omega E dot. Well, and this can be proven by, let's see, taking this one, this quantity here, and apply the transpose to everything. And you can, because the result of this, it's actually a scalar. So you can easily transpose a scalar, nothing's going to change. But the rules about transposing products of matrices and vectors tell me that the transpose of that is 1 over 2 omega E transpose J is a symmetric matrix JT omega E dot. Agree? And so you have two identical terms, you add them together, the two goes away. All right. So there's that. Then we have the quaternion piece. I have twice E transpose E dot, same story. I am taking these, and the derivative of this term E transpose E is going to be E transpose dot times E, and then ET, which is not the extraterrestrial, E transpose E dot, transpose the second product, because you can, it's a scalar, and with the same approach that we use for this term, you get twice ET E dot. Then I have minus 2, 1 minus E4 dot. This is the time derivative of 1 minus E4, everything squared. All right. You can show that, let's see, you can show that E dot, this term here, is equivalent to 1 over 2 E skew symmetric matrix applied to the angular velocity error plus 1 over 2 E4 omega E. How do you prove that? I'll leave it up to you to do, but it's basically just kinematics. So E dot, and remember E is only the first 3 components of the error quaternion. Okay, this is how I defined it. First 3 components of the error quaternion. By using the kinematics equations with quaternions, you can prove this expression. Very useful. And likewise for E4 dot, you can prove that this is minus 1 over 2 E transpose omega E. Go ahead and show it to yourself when you have time outside of class, but you have all the information to do so. It's basically, again, the kinematics of quaternion equation. It's just manipulating that a little bit. So this is going to give me, what do I have? Well, I'm going to collect omega E transpose 1 over 2 JT dot omega E plus JT omega E dot. Then I have, I'm going to collect E transpose between, let's see, yeah, between this term and this term, because E4 dot will become minus 1 over 2 E transpose omega E. So in other words, I have E transpose that multiplies EX plus E4, and this multiplies omega error. And then last term is 1 minus E4 multiplies E transpose omega E. So there's this term that is simplified with this term, because they multiply the same quantities, except there is a minus. Then continuing, simplifying things, I have omega E transpose 1 over 2 JT dot omega E plus JT omega E dot. I'm left with ET omega E plus ET omega E. I'm going to, again, this is the same, I'm going to transpose this term. And so, no, not yet. I'm actually just collecting things. Collecting omega E. So E transpose EX plus ET multiplies omega E. And if I transpose the whole thing, which I can, because again, these are all scalars, I get omega E transpose EX transpose apply to E plus E. equals something. What is this giving me? Ideas? It's a skew-symmetric matrix built with a vector E transposed and multiplying E. What is the transpose of the skew-symmetric matrix?
It's minus the vector product, so it's 0.
Right, so it's minus EXE, which is 0. Yeah, good. So I'm left with omega E transpose that I can collect 1 over 2 JT dot omega E plus J total omega E dot plus E. Now, this is the time derivative of the Lyapunov function coming from the actual definition of the Lyapunov function. But I also wanted this to be this expression. Remember, this is what I want. Yeah, actually, yeah, I wrote it here. This was my desired behavior. So I'm going to equate the two. I'm going to say that I want minus omega E k omega E to be equal to, there was a transpose somewhere. Ooh, yeah, there was a transpose here. Sorry about that. Forgot to transpose in the desired v dot, otherwise it wouldn't make any sense. Then I have omega E transpose 1 over 2 JT dot omega E plus JT omega E dot plus E. Fine. Simplify these guys. If the omega error is 0, I get 0 equals J total omega E dot plus E, which means that the omega E dot is equal to minus JT inverse times E. Good relationship. This is what's happening if I define that candidate Lyapunov function and I try to impose that its time derivative follows that expression. So with this, I can go back into my third time derivative of the Lyapunov function, which is somewhere here, right here. Okay. And see what happens on omega E equals 0. So let me rewrite it. So I have to check what happens to the sign of this expression, minus 2 omega E transpose dot k omega E minus 2 omega E transpose k omega E double dot. So I'm going to compute this for the relationship that I just found, which is omega E dot is equal to minus J transpose inverse omega E, A E. And second condition is that omega E is 0. Well, that means that I get V triple dot equals minus 2 omega E transpose dot k omega E dot. Did I miss a dot? Something is not computing well here. Did I miss a dot somewhere? Yes, I did. No one noticed. Okay. When I wrote the third time derivative of my v dot. Okay, that makes sense. So that's what I'm left with. Now I have this expression for omega E. So in other words, this is going to boil down to minus E transpose JT inverse transpose K JT inverse E, which is definite negative, because these are all positive definite matrices. Doesn't matter that you're transposing them, inverting them. So you can call this something else. You can call this bunch of matrices just Q, and it's a symmetric positive definite matrix. And there is a minus here. So this is proving that the Lyapunov candidate function I defined, and the desired for me to have it so that V dot is equal to this expression will be stable for both the angular velocity and error and the quaternion error. Okay. All right. So I think we can take another 5 minutes here before we actually start working on deriving the controller itself. Any questions?
Yes, Professor, sorry, but I didn't understand too much the meaning of Lyapunov function. Okay, probably by summing up, we are trying to find a function that satisfies that two conditions, because we are sure that if that two conditions about the first derivative and the third derivative are satisfied, we'll ensure that both quaternion and both angular velocity and attitude are stable in some way, are controlled stably in that sense. No, this was my. We know that a priori this condition will allow us to control in a stable way.
Yes. So
okay.
So we haven't derived any controller, but I am suggesting that my function of reference is this one, and then I want its time derivative to behave like this. If now, and so by imposing this Lyapunov function and this behavior for its first time derivative, and I've been shown with all this math that this is okay also for the error quaternion when omega e goes to 0. If I can make this happen in particular, then my system will be Lyapunov stable. In other words, this function that contains all these error combinations obviously will go down because its time derivative is negative. And so in turn, the errors will converge to 0. Now it's up to me, having imposed this function, and in particular, this behavior for its time derivative, to find a way to make it happen. So now I have to find a way for the omega error and E to follow this behavior. And so that's basically the sign in the controller now. So I'm going to substitute the error dynamics, in a sense, inside my equations of motion and see what happens. Okay?
Okay, thank you.
Yep. Okay, shall we resume at the 40-minute mark and go for another 20 minutes?
Okay.
All right.